Finally, it's time to move from feed-forward networks to recurrent neural networks. This represents a relatively minor change in the architectures we're looking at, but an enormous change in the vocabulary with which we seek to interpret and view the networks. Time now becomes something we need to think about. In the feed-forward architectures, links go from input to output in a cascade that may have many layers, may have many connections, but nothing leads back from one site to a previous site. All connections are forward. When we introduce a cyclic loop into the architecture, for example here one unit connects to itself, we have a recurrent neural network. Now, we've seen some recurrent neural networks in the interactive activation system, for example, and there are many architectures around. And they were introduced in the they were always there with neural networks, but when backpropagation caught on in 1986, recurrent architectures were viewed as being very difficult to train. The same procedures, the same kind of gradient descent procedures that were used so successfully for feed-forward networks did not translate without problem to recurrent architectures. That situation has changed in the meantime, but we won't be keeping up with the latest and greatest as usual. Because time now plays a role, we can choose to view a recurrent neural network as we have viewed feed-forward networks, but we can also view it in a different way, as a dynamical system which has a particular state, the set of numbers that characterize the network, at time 0, and a state at time 1 and a state at time 2. The state is understood to include everything about the network, all the numbers that describe the network activations, weights, parameters, the whole lot. Some of those change more quickly. The activations will change at every clock tick. During training, the weights will change now and again, but if we're only testing a network, it's only the activations that change. Now, the state at time 1 depends on the state at time 0 and at the input at time 1. The state of the network at time 2 depends on the state at time 1 and the input at time 2. Because the state at time 1 already depended on the state at time 0, the state at time 2 depends on not only the previous, but the one before that, the state before that, and so it goes. This is a discrete dynamical system because time has been chopped up, as if time came in slices like this. It doesn't. But in a digital world, such tricks are very, very common and usually quite profound. We won't be digging into the profundities too much. We're going to use a very simple form of recurrent network, the only one that's available to us in the BackProp simulator. It's known as a simple recurrent network, or sometimes as an Hellman net, after Jeff Hellman, who was the first to employ this architecture. And the basic idea is shown there on the screen. I've only shown one input and one output. There could be arbitrarily many. There's one hidden layer, and then there's something new. We have what's called a context layer. And the way this works is different from all the other layers we've seen. When input arrives at time t, we place those numbers in the vector x of t at the input units. We then calculate the values of the hidden units and then at the output units. But staying with those hidden units, we then copy those values unit for unit to an additional layer. Those are not those are inappropriately shown in the diagram. There should be just one line from each hidden unit to each unit in the context layer. And those are not connections with weights. That's a simple copy operation. So that the next time at t+1, when we present input, the hidden unit will compute its values based on the input, but also based on its values at the previous time. So this is a slightly clunky way of implementing a link from each hidden unit to itself, or more appropriately, from each hidden unit to all the other hidden units, including itself. The copy business and the business of putting an extra layer allows us to still use feed-forward computation. But what's being fed forward is a previous record of the internal state of the network, not the whole state, just the hidden layers. The bias units are not shown in this for simplicity. The introduction of this cyclic nature, such that the hidden unit activations now are computed based not only on the input but on their own previous state, changes this into a dynamical system. And we need to understand the values as they change within the network as they are spread out over time. Dynamical systems will occupy us for the remainder of this course, and it provides a very different set of tools and concepts for modeling cognition and behavior, and we'll only have the smallest points of access to it. We enter this world through the recurrent network, and then we'll explore the concepts and tools of dynamical systems just a little bit more. Incidentally, nobody knows whether you should say dynamic or dynamical. It doesn't matter. There's no right answer. But first we're going to work from our established intuitions that we have honed in the field of feed-forward networks. We're going to use as much as we can of what we've learned so far in order to understand the basic notions of state and change in the context of a recurrent neural network, and then we'll branch out into other areas of dynamics. So the task that we're going to introduce here was the subject of a very influential paper by Jeff Hellman in the 1980s, using a simple recurrent network. And all kinds of claims, as usual, were made, and most of those turn out to be somewhat overblown when they're examined. Basically, there was a set of simple English sentences taken from a simple narrative. One of the sentences would have been, many years ago, a boy and girl lived by the sea. The input consists of sequences of letters, suitably encoded, of this nature without any spaces, punctuation marks, or anything else. And the network is given a slightly odd task that is only possible now because it has its prior state available to it. Its task at each stage is to predict the next symbol. Looks impossible. Is impossible. But it's possible to do better than nothing here. So having seen M, the network is tasked with predicting A. Now there are undoubtedly other M's in this data set, and they're not all followed by A. So the task is in principle undoable. However, having seen, for example, the most recent letters Y-E-A, the number of letters that can follow that plausibly, given the statistics of the data set, is very, very limited. And it might be possible to predict, perhaps with 100% accuracy, that an OR is going to follow the letters Y-E-A. So we've gone from using networks to make firm decisions, categorize things, and so on, to a network that can only ever do probabilistic kind of prediction. The architecture is this very, very simple architecture. It's constrained, and no explicit information is given about what kind of sequences of letters are available in English. Now, the manner in which this network is spoken about is somewhat indisciplined. Jeff Hellman described it as a phoneme predictor. Letters are not phonemes. This is not a phoneme predictor. It's a bad label. Letters are letters, and English spelling, as we've seen, is a disaster. which makes this task, of course, even harder than it might have to be. So what is at stake here? At stake is the use of sequential input in which the output is conditioned not just by the present input, but by the past states of the networks. And we have a novel task structure in which we're trying to predict something which can't be predicted with perfect accuracy, but where we can do better than nothing, precisely because over the data set, the training set as a whole, there are sequential statistics. You could count all the letters that occur after an M, and maybe 50 of them are A's, and 20 of them are I's, and 3 of them are E's. In that case, the network should make it quite likely that an A was presented, less likely that an I was presented, less likely still that an E was presented, and the network should rule out that any other letter might come next. What's not at stake is any substantive claim about language. There's no realistic language modeling here. Letters are not phonemes. English spelling is just a complete mess, and the database is a few sentences. It does not stand for the whole of English grammar. So let's have a look at the kind of results that were obtained here. Shown on the y-axis here is the root mean squared error at each point in the prediction. And you can see that the error, as we work our way through the sequence, doesn't remain constant and it doesn't fall. This is for a trained network. Rather, the trained network still generates tons of error because the task is in principle, you cannot predict with certainty what the next output is, but you can see that within a word, as we move through the words, having seen an A and a G, for example, the chances of the next letter being anything other than an O are probably very slim. And so the predictiveness, the likelihood of being able to say anything about the next letter gets better. Our ability to make statements gets better within a word and then resets at word boundaries because this has no grammar. Having seen the whole word many has no idea what's coming next. It happens to be many years. Maybe it was going to be many boys, many girls. So after the final Y of many, it has no clue what to predict. And so you can see this characteristic error curve, which suggests that the network is responding sensitively to the sequential statistics of the training set, and thereby revealing things like word boundaries. So what was learned here? Well, we said the task is not perfectly solvable. What we're more interested in is this variation in the error. The uncertainty is highest at word boundaries and error goes right back up then. But depending on the statistics of the letters, not phonemes, in the training set, prediction to a limited extent is possible. Not all word boundaries show up. So in the previous slide, let's go back and look at it. There should be a boy many years ago. A boy is treated as one word. That is to say, after A, it predicts B, and then O, and then Y. There's no recognition by the network that a boy is anything other than a single unit. Now, as it happens, we make such mistakes sometimes. So you may hear kids speaking about an elephant. The word is, of course, elephant, doesn't have an N at the end, but when we use the indefinite article and say an elephant, it's possible to mishear that and think it's an elephant. Something similar happened in English in the development of the word nickname. Nickname used to be called eek-name, E-K-E name, but an eek-name became a nickname. And they're fossilized in the language. So such confusions have some kind of plausibility about them. They chose to represent letters in the most primitive way possible, no similarity relations whatsoever, purely localist representations. So, what should we say about this? Well, we should say that this bears little or no relation to what a child is doing when it's learning language. The representations that are available to children are far, far richer than the single 1 or 0 of a localist representation. Phonemes, after all, group into classes. They also form part of syllables. Syllables have information. There's non-segmental information in the rhythm, in the melody, in the voice quality, and of course a ton of information in the context in which speech is spoken. None of this features at all in the network. Another way to look at it, and this shows you how squishy the topic of representation is that the representations available to the child are much poorer. The network is given a symbol at a time. Children are not. All the sounds run together and they have to parse the world, first of all, to separate out linguistic from non-linguistic, and then to sort out what's in that linguistic mess. So the world doesn't arrive neatly chopped up, parceled and discretized for the child. The task that's involved here is a new learning paradigm for us. We haven't seen a network like this. We've seen some odd tasks, and the task that you set a network influences how you view the network, what you can use it for. So auto-association was very different from categorization, for example. This task of predicting the next symbol doesn't seem to be a good behavioral description of what children are doing at all. Nonetheless, as we become acquainted with languages, we develop very strong expectations of what will follow what. And when those expectations are violated, we seek the cause. It could be argued that you don't need a neural network really to analyze the sequential statistics of a data set like this. You could just count things. So you could dig in, for example, and find that after the M, 50% of the time it's an A, and 50% of the time it's an O, and it's never anything else. And the best trained network will eventually arrive at the same conclusion. But it's the induction of a set of weights that is sensitive to the statistical distribution of the symbols, and where the performance of the network then reveals other aspects of the structures in there. So word boundaries, for example, are nowhere represented in the input, but we can see them then in the variation of the error term. The prediction task is interesting. It's one way of thinking about error-corrected learning without having a godlike teacher, as we have in backpropagation. In backpropagation, we have inputs, and we decide, long before we ever build a network, what those inputs should generate at the outputs. That's biologically entirely implausible. It has nothing to do with biology. Prediction, however, is a way that people have been using of late, and increasingly so, of suggesting what biological systems might be about. And in particular, there is a substantial movement in cognitive science that views the brain as a kind of a prediction machine, always trying to predict the sensory consequences of its actions and then noting mismatches and correcting in a cybernetic sort of loop. I'm not a big fan of it myself, I must say, but it's a very important paradigm which a lot of people are taking seriously. Notice that auto-association, although trained by BackProp, also didn't use this godlike character of the supervised learning expert who knows already what the answer is. Both approaches train without an explicit set of target outputs for the input patterns that are separate from the input patterns. And so they both open ways to for theorists and modelers to consider different ways in which we might consider the progress of a learner as they develop a skill or a competence in an area. So that's our brief introduction to recurrent neural networks, and we'll be doing something similar to the phoneme prediction task in lab.